Gustavo, ¿ya volvió del mismo link? Es el mismo.
Okay, oh, no problem. Okay, so I'm first going to talk a little bit about the Peru flat slab, and then I'm going to talk about the Pompeian flat slab where we are. So the Peru flat slab shows the Nazca Ridge coming in, and right in front of it is the Fitzgerald Arch. It's an uplift. It's a broad uplift. There's no faults at the surface, so it's very different than the Sierras Pompeianas. But it seems to be right in line with the subducting Nazca Ridge. And so here's the seismicity again, and you can see the green, and then there's kind of a gap here, or at least a lot less. These are magnitude 4 and greater earthquakes from the USGS. Here's the ridge coming in, and this black outline is the mirror image of the ridge on the other side of the Pacific that people think has subducted. It's a projection of the conjugate ridge. So it may have gone down quite a bit. So I'm going to talk about receiver functions, and many of you might be familiar with them because Patricia did a lot of receiver functions. But we're going to use P to S converted waves. So a P wave comes up, and when it hits a discontinuity, it converts to an S wave. And we can process the data to highlight those. And what we end up with is something as a function of time, the direct P wave, a P to S conversion from the continental moho, maybe a negative P to S conversion from the top of the oceanic crust because the velocity decreases, and then another positive for the oceanic crustal moho. And if we take teleseismic earthquakes coming up under our stations from all different directions and azimuths, we can put together a three-dimensional volume that shows us discontinuities. It's not seismic velocity, but it's discontinuities. And here's one of those images going across the Andes where the Nazca Ridge subducts. And red is an increase in velocity with depth, and blue is a decrease. So it's a little bit like reflection data, except instead of reflection data going down and back up, it's just coming up. And so right away you can see this dark red we think is a continental moho, and this red we think is the slab moho. And look how close together they are. And the Nazca Ridge studies offshore show us that the Nazca Ridge has oceanic crust 18 to 20 kilometers thick. So this is right up against the base of the crust. And then this sort of ends, and we don't see it going subducting back down until we get way over here. And then from other studies I'll show you it starts to subduct. So I said usually if the when that transformation happens and it's eclogite, it should be dense and want to go down. So right away we have something holding up that flat slab in Peru that's different from the situation in Argentina. And the other thing we've noticed when we look at other profiles is that when we see the slab, there's a lot of tears or offsets in it. And so we think that the slab under Peru is starting to break up. And the continental moho, right where the ridge is coming in, is 55 kilometers thick. And let me just show you a map, and let me explain this a minute. This is a map. Here's the Nazca Ridge coming in. It's the separation between the continental moho and the slab moho. And this contour is 20 kilometers, and within that it's less than 20 kilometers. That's the thickness of the oceanic crust. And it's thinning the continental crust above it. And it looks like it's displacing the mantle lithosphere and crust, pushing it out of the way, out under the Fitzgerald Arch to cause that uplift. So that's a little bit different than what we're seeing here. And it means that this mid to lower crust is, I guess, soft enough to be pushed out of the way. So here's where the ridge was 4 million years ago. Here's where it is today, and it's going right through that region. And this is a map that we've made of the depth to the continental moho. And you can see that it gets, as you go down to Bolivia, it's 75 kilometers thick. It's 70 or 75 up here, but right in here, it's maybe 50 kilometers. So it's probably sliced off even some of the lower crust and pushed it out into the Fitzgerald Arch. And we don't see anything like that here with a Pompeian flat slab. And so this diagram sort of shows what that might look like. The arch, it's only 500 meters high, but it's got an area of about 4 times 10 to the 5th square kilometers. There's no surface faulting, and it would take if you shoved about 5 kilometers of crust under it, you would get this elevation. And it's a little maybe hard to see, but this is where the 100-kilometer contour is for the Nazca slab. And we just modeled it with an indenter, like this green box. And the purple lines are contours of what you would expect the new crustal thickness to be. And it matches with the Fitzgerald Arch. Now, we don't have any seismic data from that arch. It's down in the jungle. So we can't measure that crustal thickness. So it's an idea, but we know that there's a lot of missing material. And this would be one place to put it. And a lot of models have suggested that this is the case. Axon et al. In 2018 did a thermomechanical model for the western US, the Laramide, with a flat slab that you can see that extended under the western US. And they suggested that there was a keel that got bulldozed over. It's sort of similar to what we're suggesting. We use a lot of different types of seismic data and methods, because if we see something in several methods, we tend to think it's more robust than if we just see it was one method. So this is a different scale tomography. It's velocities now, not just continuities. And it's from surface waves, both earthquake-generated surface waves, earthquake-generated surface waves. And so I'm going to show you 3 different cross-sections from southern Peru, across where the Nazca Ridge goes, and just a little bit north of it. And in the south, we see high seismic velocities in blue. These are S-wave velocities. And then we see slow velocities in the mantle wedge, just what we would expect. But as we go up to the next cross-section, suddenly we see a dipping structure that looks like the slab, and we see maybe a flat slab under here. But over here, we see, we don't see anything. And then we see these very low velocities under the flat slab. And we've suggested that these low velocities, it's almost like a mini plume that's holding the flat slab up in Peru, because it extends so far. Again, we don't see that so much here, a little bit. And then as we go further north, suddenly we see, even though we think the slab is still flat, for the most part, we see this thickening structure. And it suggests to us that maybe the slab is broken off. It's starting to resubduct. There's still a bit of flat slab in there. And then this might be the remnant slab. So at this scale, we're seeing the slab break up just on the north side of the Nazca Ridge. The Nazca Ridge is probably holding it up, and then it's starting to sink and it's breaking. Now, if we step back and look at another scale, as you see, I like to look at things at a lot of different scales. This is down to 1,200 kilometers, and this is 2,800 kilometers across. Here's the Andes and the Peru flat slab. You can see the earthquakes. And this is teleseismic tomography. So using P waves that are coming up under South America and using about 1,000 data from about 1,000 stations in South America. And the blue is high velocity and the red are slow velocities. And these are percentage rather than absolute velocity. But you can see that the blue goes almost vertical and then it flattens out at about 1,000 kilometers. And a lot of people think at 1,000 to 1,100 kilometers, there's a big viscosity contrast. So the slab can't get down anymore. And then we kind of lose it. It's breaking up, probably resolution, because this is out in the Amazon and there's not a whole lot of seismic data. But it's nearly vertical. So here in red is that low velocity zone, and you can debate how deep it goes, but it's really a low velocity right under the flat slab, holding it up. So when that slab bends and goes down vertically, to bend at 90 degrees seems like the slab has to be pretty weak. And maybe it's weakened from that low velocity under it, but it has to be strongly coupled at the top in order to scrape off the mantle lithosphere and push it out of the way. So here's our sort of summary cartoon of what we think might be happening here with the Peru flat slab, and I've said a lot of this, so I won't repeat it, but important points are that it sliced off some of the lower mantle and crust, and the flat slab is right against the base of the crust, and it extends over 200 kilometers. It extends almost 200 kilometers before it resubducts. And this low velocity zone is probably keeping it up, adding to the buoyancy. And then, of course, to the north, the slab is breaking. Okay, so now let's get to the Pompeian flat slab where we are. I've said there's high rates of seismicity. The upper plate has a lot of faults that seem active. There's some debate about whether they may have been pre-existing zones of weakness prior to the flat slab, but they seem to be activated by it. So here's another map of seismicity, and again, you can just see no matter how you plot it or what earthquakes you use, all of those red earthquakes, most of those are in the flat slab. And here's a cross-section of the flat slab, earthquakes from one of my former students that worked a lot with Patricia, Leopold Linkemer, and you can just see how flat it is, right about 100 kilometers. The arc is shut off. This is the south end, I believe, of Pier de Palo. The arc shut off somewhere around 5 or 6 million years ago. Some of you may know the details better than I do. And of course, we know the Juan Fernandez Ridge is subducting along here. So more recently, Ariana and Steve Riker and his group at Rochester, working with folks here, and in fact, Steve will be here soon, going back with some of the previous data that we collected, Siembre and ESP and IMPRESS data, they were able to use one of these automatic pickers, and now people are using machine learning to find PNS waves. Students used to hate me for telling them they had to sit there and pick PNS waves forever. Leopold's study had about 2,000 earthquakes. There were many more, but that was about how many he could sit and pick without going nuts. Well, they found 36,000 events that they could locate. Look at that. Here's another cross-section. It's just this little spot right here, using all of this pre-existing data. And I just mention that because every time we collect data, this data is here forever, and new things will come up that you'll do with it for, the next 20, 30 years. Look at all these earthquakes. I mean, look at these earthquakes. So in this recent paper that Patricia was part of and Sol from here, and Deanna and I, but really led by Ariana and Steve, suggested that these earthquakes are from, dehydration reactions, which we know, but there's so many and they're releasing so much water that they manage to get up through the mantle lithosphere, and it's basically hydrofracking the crust. Because when you go to the eastern part of the Sierras Pampeanas, there are not as many crustal earthquakes. So that's why I said when we had the little break that all these earthquakes in the slab may be causing earthquakes in the crust. And so we'll have to see. This paper just came out. We haven't heard too many people disagree, but you never know. So just a little bit of background, and again, many of you know this area better than I do, but there's a series of accreted terrains across here, and here's a schematic cross-section. The crustal thickness is a little too deep, I think, but there's a number of versions of this in the literature. And so we've always been interested in trying to understand that structure a little better. And the arc shut off, if you plot up data, this is from a paper by Alderall, 2020, but many people have done this using ages in some of the databases. So this is longitude and this is age. You can see that the arc is going along. Something happens at about 24 million years where it starts to go inland, but it really starts to go inland and shut off at about 5 million years. So there's a lot of good evidence that the arc has shut off, as we know, and that's always been evidence that the slab has gotten flat. So again, if we go back to receiver functions, we can see the same thing again. Here's the top of the oceanic crust, here's the oceanic moho, and then the continental crust is sort of this line. It's a little weak in spots, but that's going across the flat slab region. And again, the oceanic crust signal ends, and that's about where the slab starts to resubduct, and I'll show you some images of that in a minute. So here it sort of works out that when the oceanic crustal signature disappears, that means it's got the same velocities as the surrounding mantle because it's now eclogite instead of basalt. It tells us where that happens. Well, okay, let's step back again now. And I mentioned all those earthquakes being due to dehydration. If we look offshore, back in 2001, we happened to have stations out in Chile and Argentina, and we recorded an earthquake in the outer rise out here. And because we had all these stations on shore, we could locate it and locate the aftershocks. It's not perfect because we didn't have any stations out in the ocean, so we had less than 180 degrees, but we still did pretty well. This was work by Robert Fromm, a student, graduate student we had from Chile, who's unfortunately not with us. But what he found was that this earthquake, all the aftershocks located below the oceanic crust in the moho, or in the mantle. And there were two planes shown by these red lines. And it was so deep that we think the seawater could get down into the mantle. And that's what you need. You need to get water into the mantle in the outer rise to really hydrate it. And when you do that, with earthquakes like this, you're gonna make it more buoyant, and you're going to then have water to, when you dehydrate things, you get that water back up into the lithosphere. So when this study came out, there wasn't a whole lot of, it didn't make a big splash, but it's been cited a lot lately because it shows how deep some of these outer rise faults go. So it just goes to show sometimes when you do something and you think, oh, well, it's interesting, but then later people say, wow, that's really interesting. So this is some really good evidence for oceanic lithospheric hydration. Now, work done out of Patricia's lab with John Batiste, that many of you know, and again, unfortunately, is not with us. He did some joint inversions with receiver functions and surface waves. And these are cross sections. The top one is his image, and this is the oceanic crust that's slightly lower seismic velocity. Here's the continental mantle, the dark blue, and then the continental crust above it. And then below are some of his interpretations. And these are earthquakes that Leopold had located, and some of the focal mechanisms. Most of them are normal faults, but not all of them. And again, he was able to image a pretty good oceanic crust going across. And one thing you'll notice, again, is with the crustal earthquakes from Leopold's study, a lot of them are right above the flat slab, and then you can see some of the earthquakes start to dive down. So we can see where it starts to, where the slab starts to resubduct. And these earthquakes that go down to 35 or 40 kilometers, that's really deep for crustal earthquakes. That means the brittle ductile transition is depressed. Normally you get ductile flow starting with quartz at 350 degrees and maybe feldspars at 400 maybe. But say in many places that transition is at about 18 kilometers depth, maybe 20, but not 35 or 40. So to me, to us working in the US, these are really deep crustal events that just, it has to be pretty cold to get all those. And then most of the work we've done shows that the lower crust has fairly high seismic velocities. And in fact, some of the modeling shows that it's partially eclogitized. So maybe you've shoved it down, it's starting to transform and be dense, and it's holding down the surface elevations, because if you look at the crustal thickness, it's not in isostatic equilibrium here. It's not, it should be higher for the crustal thickness that we see. There's always a little trade-off there. But it normally, if it becomes eclogitite, it's gonna drop off and delaminate or something, but the flat slab is in the way, it can't. But when that flat slab moves, you might see something happen here, or that's what I would predict. And here's another surface wave study by Ryan Porter, and this is just a depth slice of the seismic velocities at 110 to 120 kilometers, and the blue is high velocity. So that's the slab sort of normal dipping, and then this is the flat slab sticking out. And again, it's just another way to look at these with another data set. And these are the cross sections that I wanted to get to, and mainly to show that here's the slab going down, and then it starts to resubduct, and here's the corner flow that started up here. There's not much volcanism out there, but we think it's because the slab has already released the water, so it can't release more water deeper that would normally enhance melting, give you arc magnetism. And this seems to be typical in flat slabs, that the volcanism moves inland, but then you don't get like huge stratovolcanoes, you know, a whole new arc too far inland, because at some point it doesn't have more water to release. But the thing that I put this in for was, you know, the slab comes down, it has to bend to go flat, and then it has to bend again. And some of the seismic parameters we see suggest that when it bends this one, it's putting that slab into compression, and the fluids can't get through. But then when it flattens out and starts to bend the other way, it opens up the faults a little bit, and fluids come out. So we see hydrating mantle here, and maybe not so much there. Oops. Probably still to be worked out a little more, but this was Ryan's idea when he studied this part of the flat slab. So the hydration and how much water gets released is partially dependent upon the slab bending, or, you know, it bends and then it unbends. And you don't wanna, you wanna still take into account the bending as it flattens out at 100 kilometers. Okay, let's step back again to a larger scale and work that Daniel Portner did. And again, Patricia's been involved in every one of these studies. This is a map view at 320 kilometers, and blue are high velocities, and yellow or reds are low seismic velocities. And here's our slab. Stepping down, we've taken a slice, and then there's this big gap with some red in it. And if you look in cross-section, here's the deep part of the slab, here's the slab, and there's all this red through here. And so it looks to us like this is a big tear down pretty deep, and right at the southern edge, maybe it starts around 200 kilometers, and there's actually mantle flowing through it, or at least there's slow velocities there. And whether, there's two ideas. One is that mantle gets entrained under the slab as it's moving. The other is that it would be a plume coming from the transition zone up. And we don't know which it is. A lot of studies have shown in Cascadia that slow velocity mantle gets entrained or gets caught under the slab as it's moving. And then if it finds a gap, it might go through it. And just to test these ideas, we've done a lot of synthetic tests. So you see an image, but people say, well, how do you know it's well resolved? So you make a synthetic slab, a model, and then you trace rays through it and make synthetic travel times, and then you invert those travel times just like it was real data, and this is what you get, the slab going through. Now you can see that there's smearing, and our images are never perfect because we don't have perfect data sets. And then you can take a slab and put a big gap in it and invert it, and this is what you see. You see a little smearing, whoops, but you don't see a lot of red in there. But if you put some low velocities between them and then invert it, you get something very close to what we see. And so we use this to sort of argue that we had good resolution for the tomography for this pair, because it was kind of unusual that nobody had noticed it before, we thought. And then what became even more interesting is we wanted to know if mantle was flowing through it. But how do you measure mantle flow? It's always tricky, right? Well, in this part of the mantle, there's a lot of olivine. And the olivine lines up, if you've had mineralogy, there's a fast direction and a slow direction in the crystal of olivine. And so a lot of people use that, and we can measure a fast and slow direction for S waves, especially SKS phases, and in the upper mantle where there's a lot of olivine. And if there's a phenosphere in the region, like here, then we think it's probably a proxy for mantle flow. Now, we don't know if it's going this way or this way. We can just get an orientation, an azimuth. So one of my postdocs, Holt and Leonard, did this study. We took Siembre data, ESP data, data from another experiment to the north, and charge data and whatnot. And he looked at the fast directions. So up here, these fast directions, give them another study, but they're going every which way. Look at that rose diagram. They're just going everywhere. It's like chaotic. But right here, right where we think the tear is, they're going not quite east-west, but they're really lined up. And then when we go south, they're lined up 90 degrees away. So what we suggested was that this fast direction that's sort of east-west is mantle flow going through that tear, and that we can see it with this, the difference in the SV and SH propagation. One direction's faster than the other because of the olivine. And it's one of the best examples I've ever seen for changes in flow so quickly. The technique is called shear wave splitting. If you're ever interested in doing it, you can get S waves from anywhere, and there's some details, but it's not that hard to do. And we plotted this on the tomography at 320 kilometers. So a lot of these line up with where we think that gap is, where that red low velocity is. You still with me? Okay. So let's compare this scale. The top one is the Peruvian flat slab with that vertical drop, and then it flattens out. This is the one near here where we have a gap in the slab, and then the slab picks up, and as far as we know, goes on down to deeper than 1,200 kilometers. So again, very different geometries. And so, we're still working on maybe what that means in detail. Okay, let's get back to the flat slabs. So seismology is great. I've shown you a lot of interesting images, I think, of what it looks like at different scales with different techniques. but then sometimes it's good to look at what the modeling tells us. And this is not work I've done, but there's a lot of papers that are modeling the flat slab, mechanical thermal models. And one of them, Few et al. In 2016, looked at where there should, in his models, where there should be flat slabs and where there shouldn't be. And one of the big things was, he said it was slab age, so younger ages have flatter slabs than older ages. And then the thickness of the oceanic crust. And here's 5 kilometers, and here's 25. And so, the Nazca Ridge plots right here, the age of the slab is about 35 million years, roughly, a little more. And it's right there in the flat slab region. So orange is flat slab, the gray is where it shouldn't be flat. And there's this line according to his models. The one Fernandez Ridge, because the oceanic crust is not so thick, it's right on the border. Probably the hydration puts it over the edge, I think. And then here's the Kiki Ridge. That's similar age, similar oceanic crustal thickness, but it's not flat. So perhaps it's not hydrated. And then the Carnegie Ridge plots over here. And boy, should that be flat. There's 2 different ages of oceanic crust, one about 12 and one about 22 million years old. And yet, although I haven't shown you it, I've been doing a lot of work in Ecuador since 2016 when they had that magnitude 7.8 earthquake. And there's earthquakes dipping down in a Wadati-Benioff zone, and there's an active arc, so it's not flat, but the ridge is subducting. And our work shows that the ridge hasn't subducted very far. It hasn't subducted all the way to the arc, just a little bit under the forearc. So probably in the future, as it subducts more, it will become flat, but it hasn't happened yet. But it's starting, it might be starting to, because there are 2 Ecuador volcanoes that are now pretty active in the Subandean zone, in the thrust belt. And so it looks like the volcanism is starting to migrate. It's still broad because the main arcs, there's 2 arcs there, and Quito sits in the center. They're both active, major eruptions all the time. But this gives us some insight into at least a couple of the parameters. And so I think, I like to do comparative studies because I think it shows different things and gets you thinking about what might be important. So here's our sort of summary diagram for the Pompeian flat slab. And I always tell my students, you need to make these little cartoons at the end. They're just schematic, but they convey things sometimes better than some of our complicated plots. So, we've got the slab going down, we've got all these earthquakes. We think we have mantle flow, a thermosphere through this slab window, and we've got all these high angle faults across the Sierras Pampeanas. Of course, it gets tricky with the scales above sea level are different. But again, it's different than Peru because you've got the basement chord uplifts internally. We haven't sliced off the mantle lithospheric crust, and there's a lot of deep earthquakes that are right above the abundant earthquakes in the slab. And so finally, I just wanted a word slide to make sure I said this correctly, or maybe if you read it. I think the difference in earthquakes in the Peru flat slab and the Sierras Pampeanas is really important to understand. And with Laura Wagner, we wrote a paper in 2000 suggesting that the intermediate depth earthquakes that you observe in regions with thinner oceanic crust are caused by mantle dehydration. But if the oceanic crust is so thick like the Nazca Ridge, then these reactions are not possible because you can't get water down into the mantle lithosphere and hydrate it because the thickness of the oceanic crust is too much. So you don't really get water down in that plate. And also the pressures are different and temperatures are different because of the depth of where the Nazca Ridge subducting happens. It's at as I said, at 60, 70 kilometers, whereas the Pompeian flat slab is down at 100 kilometers. In normal oceanic regions, where oceanic crust is 6 to 8 kilometers thick, you get a lot of hydration because that's not very thick, and you can get faults that cut through it, and you get plenty of water. It goes down to typically 100, 120 kilometers, dehydrates, causes the melting in the mantle when you add the water, and it's the source of the arc volcanism. So I hope I've shown you that there's some big differences between the Peru flat slab and the Pompeian flat slab. The Peru flat slab is really strongly coupled to the base of the crust to the point it's scraping things off. The Pompeian flat slab I don't think is that well coupled. I think it's going on down. There's earthquakes, but they're not shear earthquakes, like it's coupled. And it's probably causing end-on compression, which gives you the thrust faults and things. And the Sierras Pompeianas faults, some of them may be new, but many of them are probably reactivated from older structures. Both flat slabs show signs of tearing, different depths and different ways, but it's just that maybe flat slabs start to fall apart at some point and eventually begin to resubduct, because flat slabs don't last forever. They're common in geologic history, but they don't last forever. So there's got to be some way to get them to resubduct. And then finally, Ariana and Steve's idea, I think, is very interesting, that those earthquakes in the slab are really almost like they're fracking the crust above it, and maybe the source of those deep earthquakes where we are now. So I just want to mention now, just very, very briefly, that we started a new project called Tango that we're very much involved with the folks here at the university in the Seismology and Tectonics lab. And this is a project that Patricia and I worked on for about 4 years to get funded. And you know, that lesson there is be persistent. It takes that long. And just when we were starting, unfortunately, we lost her, which was certainly a big blow to me, and I know we all arrived at the worst possible time to start it, right after she had passed. But everybody stepped up and helped us, and every time we went in the field, we all thought, oh, Patricia should be here with us, but we know she's watching out for us, and it all kind of worked out. But the goal of this project, which is by far the most ambitious project anybody's done in the Andes when it comes to seismology, is to look at northern Chile and Argentina, where there's a lot of shortening, maybe 300 kilometers or more, depending on who you quote, and compare it to a region further south where there's a lot less shortening, and where the Andes are thinner and they're not as high. And what is the difference in, what's causing the difference in how the upper plate responds? And not just in these regions, but all the way through. And there's a lot of ideas about what's driving that along strike variation. And we sort of proposed that maybe it was lithospheric shortening processes in the lithosphere and the crust, and lithospheric removal and end-on compression. But there's also ideas that mantle processes could be driving it. So when you have subduction, it's going to pull, well, if we're looking at it this way, it's subduction. It's going to pull material down and shorten the overriding plate. And so we're looking to image the Chile and Argentina, the West Coast, all the way down to 1,500 kilometers, even in more detail than we did. And so this has been a big project with a lot of people involved, so many I can't really put them all on a page, but there's a lot of institutions and people involved. And I'm just going to mention the seismology part. There is a whole geologic component of thermochronology and petrology, and I can talk about those if you want. The petrology and geochemistry is interesting because our colleagues have calculated paleocrustal thicknesses going back to the Jurassic time, which I find fascinating that you can do that. But anyway, I'm not an expert in that. But what we did was we put seismic stations across the Andes, and this line with the sort of turquoise color goes from the coast all the way over past Salta. And that line has 300 seismometers. And if you want to know the details, talk to Martin. He was out there for many months. And these are little seismometers like this that you just stick in the ground, you orient them. It looks easy, right? It's great. But the batteries only last 30 days. And 30 days is not enough time. So we recorded for nearly 5 months, maybe a little more, and somebody had to go to those stations and either swap out the unit and take it back and charge it on this rack that we brought with us, computer and rack, or in Chile, we had a different kind of sensor where you could swap the lithium batteries every month. But somebody had to go to all 300 of those stations every single month, dig them up, swap it, put them back in. And you guys know better than I do that this is not just a short little jaunt. That's across the whole Andes. And then the yellow diamonds are broadband seismic stations that record with solar panels and batteries. They recorded for almost 2 years, 22 months, as sort of a backbone. And they're spread out to image things that are much deeper. And then just because we didn't want to make it too easy on the students, after five and a half months up here, we moved these nodes and the rack and everything down to San Juan, and then we deployed them down here at about 36 degrees south, a little south of Malagüe, and did the same thing. It was 260 nodes instead of 296 because the Andes are a little narrower, but they still had to be swapped out every month because the batteries would die. So again, a tremendous amount of work. And then we put the broadband stations along there and out here and to record deeper. So we had a lot of fun in the field. A lot of people were involved both in Chile and here. We had groups from Salta, of course, from the University of San Juan. And we just finished pulling out all these stations in the south, the broadband stations, the last few weeks. And on Friday, we got them on a truck to Buenos Aires, heading for customs to export. And boy, did that feel good. I'm still celebrating because for 2 years, this has been a huge effort by so many people, and I can't thank this group enough for all their efforts. And now we've got data. It's about, all the data put together is maybe 13 terabytes of data. Yeah, and I didn't mention that in addition to this, we had folks here and folks in Salta. They did a deployment in San Juan and Salta in the city for site response and hazards. So that was another 1.25 terabytes for 30 days, but that's enough to get a lot of site responses and do other things. So that's not even on here. That was kind of above and beyond, and I was amazed that people still had the energy to do it after everything we've been through. And I just show you one example of an earthquake from the Jujuy cluster that occurs right here in the slab. Here's a P wave going off this way. I guess my PNS got moved. And going this way, and the S wave. And you can't see much of an S wave into Argentina on the Puna. And I think that's because it's being attenuated out because of the crustal magma bodies that are there that we know about. But with different filters, we can find the S wave. But it's just to show you that we've gotten great data with these nodes. And then another very, very preliminary study by Sanka right here in turquoise shows those seismic stations. They're 2 to 3 kilometers apart, 296 of them. That's why they go from the coast all the way into the Chaco. That's why I say it's by far the most ambitious seismic project anybody has tried, to go all the way across the Andes. And what Sanka did was he used PhaseNet, which is a machine learning code that's available. It was written by the group at Stanford, and they work a lot in Japan, and it's publicly available. And you can run all the continuous data through it, and it will give you PNS wave picks. And there's many codes like this. This is not the only one, but it happens to be what we're using, and Martin is using it for some of the salted data up north. But he found 6,300 events in 4 months. This is, again, just preliminary. They're shown here. Some are in the slab. Not many events in the Puna, but then a bunch in the eastern Cordillera in the Santa Barbara belt, where it's very active, as you would expect. The depths he gets are much shallower than the USGS when we have the same earthquakes, because we got stations right on top or close by, which you need to get good depths. And I think some of these locations will get better. This is just a first cut of trying to use machine learning. But one of the things that really struck us, which I think probably many of us had suspected, there's not many crustal earthquakes in the Puna crust. It seems like it may be pretty weak. There's a lot of magnetism. We were hoping we might find more, and maybe we'll still find more. Again, this is very, very preliminary, but very exciting, because I think we're going to find tens of thousands more earthquakes with all this data, and way more in, around San Juan and the southern line. So I just end by saying thank you all for coming. And they have a fantastic seismology and tectonics group here at the university. And hopefully many of you are a part of that. But if you're like this kind of thing, there's tons of data to work with. So you should think about grad school, and you should talk to this guy or any of these people and come join us.
Thank you. Thank you, Susan. So we have some time for questions, algunas preguntas. Si quiere decir en español y las traducimos. No sé.
I find very interesting when we talk about banding and unbanding, and the water going through there. What I understand the huge difference between Peru and the Pampean Highlands is the thickness of the ocean
Crust.
Is that?
Yes, because in the outer rise, offshore, it's not related to bending so much. There's earthquakes when the slab goes in to subduct. There's what's called outer rise earthquakes. They tend to be normal fault earthquakes, as it's related to that bending a little bit. And those normal faults sort of open up conduits and seawater gets through. And when they drill oceanic crust, they see those faults filled with serpentine and other kinds of minerals that indicate there's water that goes through. And when that water can get below the crust into the mantle part of the slab and hydrates that, that's the part that often dehydrates once it bends down and goes deep. So if you don't hydrate it offshore, maybe you can't get it to dehydrate, which causes the slab earthquakes. That's a hypothesis that we're still testing, but that's what we think and wrote a paper about. So we'll see. With more work, there's always more to do to test these ideas.
I have one question about when you see the results of when you show the tiers on the slab, here in the Pampean flat slab in the Peru, came to my mind. I don't know if it's correct or not. Have you think it somehow could be related to maybe Farallon plate also with Nazca plate breaking apart, or
the Farallon plate in the past?
Well, no, because it should be subducted, right?
Yeah, it should already be subducted.
Yeah,
right.
Yeah, and it could be related somehow to Farallon, or
well, it could be. That would be pulling it down, right?
Okay, yeah.
And it could, but I think there has to be lateral variations. So like the slab is flat and then it's not. There's a lot of stress on that slab as it bends down, like the Pampean slab. So people had speculated there might be a tear, but at shallow depths, it doesn't seem like it, but as you get deeper, it seems like it. But there's gotta be a density difference. I think it's all driven by density differences. But I would say we certainly don't know exactly why. But as we get better resolution, we see more and more tears. Of course, if you don't have good resolution and you just have broad studies, then everything gets smeared out and you don't see the details. And I think there's gonna be even more details come out with Steve Riker's work with the flat slab data, the CMBRI, the charge, the ESP, whatever. They're gonna do more detailed tomography, and I think they're, I'll be interested to see if they maybe find some more details, because they've, I showed you they used some automatic picking, kind of a machine learning type thing, found 35,000 events. The study I showed by Leopold, and he has some good tomography that I didn't show, was only 2,000 events. So I'm quite excited about these new techniques to use machine learning to find earthquakes. And I think that's gonna be, well, it's already sort of the future for seismology. A lot of networks are using that to find and locate things. And it seems to do very well with P waves. S waves are a little bit harder, so you have to be a little bit careful. Some of the codes work better with S waves than others, but P waves work really well.
I have a question. I will try to say that in English. But you talk about the transformation of the basalt to earthquake, right? Does that happen in other subduction zones that there are?
Yes, it happens in almost every subduction zone. At hotter, younger subduction zones, I think it happens at a shallower depth, and older, colder subduction zones, and it happens deeper. But it happens at almost every subduction zone. It's predicted by the petrology modeling, but it's also observed with the seismology. So it happens everywhere. If you put basalt down deep enough, it's a phase change that happens.
I have a question here from the YouTube connection. It's from Rodrigo Quiroga. Thanks for your talk. What do you think about the lack of these earthquakes in the Puna, but the presence of active faults identified?
Yeah, well, I think the active faults that have been mapped out, I guess the question is how active. We're not seeing earthquakes on them right now. But again, this is 4 months, so maybe they're very few and far between. I don't want to say there are no earthquakes, and I know there are lots of faults that look pretty young there, but there's not that much erosion on the Puna. So I don't know how well dated the faults are, but certainly, there certainly are some. But right now, there's not that many earthquakes. There's a few, but not that many compared to the Santa Barbara Belt or under the arc or the forearc in Chile. And maybe the crust is really weak. The mechanisms seem to be, for the ones on the Puna, some are normal, some are thrust, some are strike slip. And there's a lot, where we're sampling, we're on the south edge of the Altiplano Puna volcanic complex, where they've imaged a very large partial melt zone between 15 and 20 kilometers that we also see. So I think it's pretty warm too, but it's a good question.
Thank you. I was very interested about you talk a new methodology with SB waves.
Yeah, it's not new, but the shear wave splitting.
Yes.
Yeah, it's not new. It's been going on for 20 years or more, maybe. But if you take an S wave from an earthquake, you can rotate it into a vertically polarized S wave and a horizontally polarized S wave. And the horizontal wave, which we call it S wave, SH wave, you can look at its travel time and the SV, and they won't arrive at the same time. They'll arrive like a second apart. And so that means that there's some anisotropy, that in one direction, the S wave travels faster than another direction. And you can exploit that and come up with the orientation of the fast direction in the upper mantle. And the idea is that the olivine crystals, if you have flow, will align in the flow. And there's models to show that. And so it's a good proxy for mantle flow. It's not perfect, but it's kind of the best we have right now.
Is there a reason why the machine learning worked better with the P waves than with the S waves?
I think it's because the P waves usually are much more impulsive, so there's bigger changes. The S waves, for one thing, we don't usually have the SH and SV rotated, so on the north and east components, sometimes they kind of dribble in. They're not as sharp, they're lower frequency. But it may work better when we have more training sets. So the idea with machine learning, in the US, people in California and Japan have taken, 1 million earthquake traces, and they've trained these codes, and I don't know how they do it, but it's pattern recognition.
Yes.
And so like in California, they've taken 20, 30 years of earthquakes, more than 1 million, and they've trained the code. So then we bring that code to South America, and we don't have 1 million well-located earthquakes to train it on, and I guess we're anxious for results. So we just use it based on the training set in California, and I think maybe the S waves might be a little different here. So there's a lot of room for improvement. And maybe someone's doing this, but someone needs to take a few million earthquakes in subduction zones and train the machine learning to do that, especially slab events and deep events. It's probably pretty good for the crustal events because California, that's what they're using is crustal events mostly. And there's maybe half a dozen different machine learning AI codes now for seismology. And it just kind of blows my mind with how many earthquakes people are finding. Sanka, he got down to, magnitude 0.5. I mean, he even has a few events he thinks are negative magnitudes. But, normally we would be sticking to magnitude 3 and above. And he's able to get focal mechanisms for many of them. So we're in this period of what we call large data sets, big data.
Yes.
Is a very popular thing, probably here too. And we're all still learning how to use big data. We need bigger computers, we need bigger hard drives, we need, more efficient codes. For many years, for me, the computers were fast enough we could do things with brute force. We could just recalculate something 100,000 times and it was still pretty fast. But now you can't do that so much. And so the combination of big data, machine learning, I think is really changing seismology fast. And it's very hard to keep up. Very hard for me to keep up. Data management has become a huge issue with these big data sets. And so anything you can do to learn about machine learning or big data is really valuable, even if you don't do geophysics in almost every field now. It's a big thing. And people in the US that are computer savvy with handling big data sets, machine learning of any type are in big demand.
Okay, thank you.
Kind of a long answer to your question.
¿Hay más preguntas?
I just want to read a comment from Sol Trap.
Oh, she's listening.
Yeah, a college from San Juan that is currently in Germany. So thank you, Susan, for the presentation. So nice to see you in San Juan. Patricia and you are a great inspiration for early women scientists. A big hug to you and the Seismotectonic team. So
thank you, Sol. That's very kind words, and I wish she were here too. I've been in the field with her several times, and we stay in touch. So we'll continue to stay in touch.
Yeah. Maybe a last, I don't know, maybe it's a comment or a question about the how is working with the Argentinian team in science.
Oh, it's fantastic. You guys have great talent, and great motivation, and I just can't say enough good things. You know, for 25 plus years, it's just been a real pleasure. And none of these studies would be possible without all the interaction with all of us, especially something as ambitious as this. And there's just so many things that I've learned from all of you, but so much I've learned from Patricia. You know, you always say a successful grad student is when they start teaching you more than you teach them. And that happened with Patricia many years ago and continued. So I think it's fantastic. You guys have so much talent here.
Thank you. Okay, so a big thanks again to you and your team at the University of Arizona, and also for all of us. I really want to also motivate the students to continue with this work. We have a lot of data now to work with, so too many years to come.
Yeah, a lot of undergrad projects. If you need a project, there's plenty of data.
Yeah.
So talk to these guys.
Yeah.
All these guys.
Gracias.
Gracias.
I just want to say one more thing. I just want to say one more thing. You know that Susan makes Patricia give to the top. It's a small